All right, so welcome back from break, everybody. Hope you had a good one. Today, we're going to start a new chapter. If you recall, the last lecture we had, we finished up current and electrical resistance. So now we're going to move on to DC circuits. But before we do that, just a couple things to announce, general announcements to make. First is that we have a new homework assignment, homework number 10. It's going to be due next Monday in lecture at the usual time. There's a worksheet, so make sure you get a copy of that worksheet up here. We also have some problems from the book. Okay, the other thing is we'll have a quiz this Wednesday, not next Wednesday. So in 2 days we'll have a quiz, and the topic is going to be what we're covering in lecture today, which is series and parallel resistors. Now, you've already seen series and parallel capacitors, so it's really not super different from what you've seen there. You know there's some general rules that we follow when combining capacitors in series and parallel. We're going to learn a similar set of rules that apply to resistors, okay? So you're going to be quizzed on that at the beginning of class on Wednesday. All right, the other thing to mention, and I already mentioned this in an email and in an announcement on Canvas, but I'll just mention it here again, is the upcoming test. Test number 2 is going to be in exactly 2 weeks. So Monday, April 4th, we're going to have the second test in lecture. And just like the first test, we'll have the entire time in lecture to work on that. So you'll have about an hour and 50 minutes. Here's what's going to be covered. We're going to have 5 to 6 free response questions, just like the first test. So there's no multiple choice or anything like that. You just are going to be prompted with a question with about a page of blank space to fill out your answer. What's going to be covered is chapters 8 through 10 of volume 2 of our textbook. So just to remind you what's in those chapters. Chapter 8 was on capacitance. Chapter 9 was on current and resistance, and we're already completely done with those 2 chapters. Chapter 10 is the one we're starting today, which is on DC circuits. Okay, so basically from now until the test, we're going to be working on DC circuits in lecture. All right? As usual, you're going to be allowed to bring a calculator to the test. So you will need that. Just make sure you bring a calculator. Graphing is fine, or you can use something simpler. Doesn't really matter to me. Also, you can use a cheat sheet just like before. So remember, this is what the cheat sheet is. It's a half sheet of paper. You can fill it out on the front and back side with basically anything you want. So it's up to you to prepare that cheat sheet before the test, because I'm not going to be providing any equations. Okay? And as usual, there's going to be a review packet. I've already made this available on Canvas. Has anyone taken a look at this already? Okay, if you haven't taken a look yet, this is what we'll spend next week in lab going over, is the review packet. All right, and then I'll post the solutions at the end of next week after all the lab sections have had a chance to go through them during their period. All right? So any questions on anything at all that I just said? Kind of threw a lot at you there, but pretty straightforward, hopefully. Okay, so then if there are no questions, let's get into the lecture. DC circuits. So all of this material that I'm presenting to you is coming from chapter 10 of volume 2 of the textbook. So you should do the relevant reading along with this lecture. And can someone just remind me, what does DC mean? Direct current, as opposed to AC, alternating current. So we'll be dealing with direct current later on in the semester, depending on how quickly we can get through the material. We'll learn a little bit about AC circuits. Okay, but for now we're on DC circuits. There are a lot of different topics here, but the first one I want to get into is internal resistance, EMF, and terminal voltage of batteries. So in a nutshell, what this is about is coming up with a sort of more sophisticated model of a battery than what we've been using so far. So far, we've just been assuming that a battery is a constant source of voltage, meaning whatever is happening in our circuit, there's just a constant voltage across its terminals, and that never changes. That's not actually the case. We're going to learn about how the voltage across the terminals of a battery can actually change depending on what's going on in the circuit and how to deal with that. So let's get into it. We'll start by defining these terms that I just threw at you. Again, we have internal resistance, EMF, and terminal voltage of a battery. So let's take them in this order. Let's start with internal resistance. So internal resistance, basically think of it this way. As current flows within the battery, it's not going to be completely unimpeded, right? There's going to be some kind of resistance coming from inside the battery that is impeding the flow of current. And we just call that internal resistance, okay? And we use lowercase r to denote the internal resistance of a battery as opposed to uppercase R, which would be some resistance coming from something outside of the battery, okay? And so all batteries do have some kind of internal resistance, and as it turns out, the internal resistance tends to increase as a battery degrades and as it has its electrodes dissolved and depleted over time. So here's how we're going to deal with internal resistance generally, okay? If internal resistance is not specifically mentioned, we can assume that R, lowercase r for internal resistance, is negligible. Okay, but if this is specifically mentioned and a value is given, then we'll have to accommodate that. We'll have to include that in our equations. Does that make sense? So unless otherwise stated, we'll assume it's negligible, but we will learn how to deal with it in some cases. And because batteries have internal resistance, the actual voltage across the terminals of a battery, it turns out, is not constant, okay? So if you have a 1.5 volt battery, let's say a D-cell battery, 1.5 volts is actually what we call the EMF of the battery. This is known as the electromotive force. That's what it stands for, EMF. And it's denoted by epsilon. So EMF is the terminal voltage, that is the voltage across the terminals of the battery, if there's no current flowing through it, okay? So no current flowing through it, you measure the voltage across the terminals, that's what we call the EMF of your battery. Okay, the terminal voltage is the actual voltage across the battery if there is some current flowing through it, which may be different from the EMF, okay? So EMF is when no current is flowing, the terminal voltage is the voltage across the terminals when there is some current flowing. And the point is, these can be different because there's internal resistance in the battery. Does that make sense? Okay, so let's now take a look at how to sort of model this. This is a simple model of a battery. So the simplest model of the battery looks something like this. You have the EMF, which we denote with this symbol. We have a sort of small line and a larger line denoting the positive and negative terminals of the battery. But then we have some internal resistance, which again, we're denoting by lowercase r. So the entire battery includes both the EMF and the internal resistance, if we want to include both of those effects. And so the terminal voltage, the voltage from positive to negative, is actually going to be across both of those components, right? Both the EMF of the battery and the internal resistance of the battery. And again, normally we hook up batteries to different devices. So whatever we hook the battery up to, we tend to call that the load. So this could be a motor, this could be a light bulb, it could be a whole complex circuit that the battery is powering. It could be whatever you want, but we just call that the load, and it has some kind of resistance, which we give by capital R, okay? So capital R is the resistance of whatever the battery is powering, and then lowercase r is the internal resistance of the battery itself. So that's the model. You've got a battery, it has an EMF, that's what's driving the current, but it also has some internal resistance which impedes the current. And then we connect that battery to a load resistance, which just represents all the different devices this thing might be connected to. That's the model. Okay. And again, the terminal voltage is across the entire battery, going from A to B across both the EMF and the internal resistance. All right, so let's work out how to do this. If we start at point A and then we go to point B, first we're going across the EMF of the battery from negative to positive. So we have positive epsilon. And then how do I state what the voltage across the internal resistance is? How does that work? Voltage across a resistor is given by?
The change, right? So V minus VA.
Yep, but I'm just asking you about the resistor. How do we write down the voltage across a resistor? It's given by Ohm's law. So it's going to be I, whatever the current is, times little r. But is it going to be positive or negative?
Negative.
Negative, because we're going with the current. Remember, that's how this works. So in total, we have epsilon going across the EMF minus I times little r going across the internal resistance. And this is what's happening when current is flowing through the battery. Now notice that this actually reduces the terminal voltage, doesn't it? Because you have the EMF of the battery, but then you have to subtract off this bit. That's voltage basically eaten up by your internal resistance, okay? So the more current that flows, the bigger I is, the smaller the terminal voltage across your battery is. Does that make sense? But if there's no current, then I is just equal to 0, and then the terminal voltage equals the EMF of your battery. Okay? But again, if there is current, you're going to get something less than that. Make sense? All right. Any questions so far? Should be pretty straightforward. Let's do a few examples with this sort of idea. So let's say we have an R equals 65 ohm load, which is connected to the terminals of our battery, which has an EMF of 12 volts and an internal resistance of half an ohm. We're going to find the current in the circuit, we're going to find the terminal voltage of the battery, and then we're going to find the power consumed by the load and the power consumed by the internal resistance of the battery. So here's the deal. Ideally, we want the power just to be delivered to the load. If we're consuming some power through this internal resistance of the battery, that's just energy wasted, and that's not what we want the battery to be doing. All right, so ideally, this power is pretty low, and this power is, almost 100% of what is being delivered from the battery. Make sense? Okay, so let's do a little bit of math then. So I'm just going to redraw that circuit again, where we have the EMF of the battery, the internal resistance of the battery, denoted by epsilon and R, and then we have the load, denoted by capital R. And just remember the way current flows in a circuit, right? If this is the positive and negative terminal, well, conventional current, which consists of positive charge, is going to want to flow away from that positive terminal like this. So in this circuit, we're going to have current going clockwise, okay? And what I'm going to do is show 2 points in the circuit, which I'll call A and B, okay? And if I want to know the voltage between points A and B, the potential difference, remember, I can go one of 2 ways. I can go across the battery, or I can go across the load. And either way, I'm going from point A to point B. So we're referring to the same voltage, okay? Going across the battery, we already did this, but we'll do it again. That's epsilon going across the EMF, and then minus I times little r going across the internal resistance of our battery. And I'm going with the current, so that's why that's a negative I times R. But again, that's the same as if we go across the load this way. Now, if we go from A to B across the load, we're actually going against the current. You see that? And that's going to be given then by positive I times big R, because that's the voltage across a resistor, but we're going against the current, so it's positive. Okay? So if we collect our terms, we have epsilon equals I times big R plus little r. So effectively, we can combine these into a single resistance, which you'll learn more about later in the lecture, but that's what it is. And the current I is given by epsilon divided by big R plus little r. All right, so what do we know? The EMF is 12 volts, so that's on top. And then we have 2 resistances to add together. We have the 65 ohm load, that's big R, and then our 0.5 ohm internal resistance. And can you just remind me, what is the equivalent unit of an ohm?
Volt per amp.
Yeah, that's a volt per amp. So you'll see that volts cancel and you end up with amps. Makes sense because we're trying to find the current after all that's flowing out of this battery. Can someone do that math for me real quick? Just punch those numbers in.
Uh, 0.183 amps.
So yeah, 0.1832 amps is what I'm getting, but yeah, we'll round it off to 3 sig figs, so 0.183 amps. That's how much current we're delivering. Okay? Okay, the next thing is the terminal voltage. So this is the current. The terminal voltage is what we'll do next. And that's basically just VAB, right? Yeah, same thing we wrote down up here. So that's epsilon minus I times little r. Now we'll just plug in what we know. That's our 12 volt EMF minus the voltage across the internal resistance, which is, okay, 0.1832 amps for I, and then for little r, that's 0.5 ohms, which again is a volt per amp. So you see this whole thing works out in volts. So what do we have?
Uh, 11.9.
Yeah, so it's 11.9 volts across the terminals of this battery. Again, it's going to be slightly affected by the current running through it. Okay? Now, the last couple questions refer to the power. So we wanted to figure out the power of the internal resistance. So that's how quickly energy is being converted to thermal energy through resistance. We'll do that for the battery itself, so internal resistance, and the load. So do you remember, how do we find out the power for a resistor? Because in both cases we're dealing with a resistor.
I squared R.
Yeah. So I'll use I squared times little r for the internal resistance. So I'll use 0.1832 amps squared times 0.5 ohms. And that works out in watts. Not going to go through the whole unit analysis. We did this in a previous lecture. But what does that come out to, everybody?
0.0167.
Yeah, so I'm just going to round that to 0.02 watts, which is pretty minimal. That's the internal resistance. So that's eating up some of our power, but not a whole lot. But the load, that's going to be I squared times big R. So it's going to be 0.1832 amps squared times 65 ohms. And what does that equal?
0.4.
We'll get something a little different for that.
2.18.
Yeah,
2.18.
2.18 watts. So that's the load. So this is always going to be something that's present in any battery. You know, you're not just going to deliver 100% of the power to your load. There's always going to be some power consumed by the internal resistance. But hopefully, if it's a well-designed battery, that's pretty minimal. And that's what we're seeing in this problem, okay? So, any questions on that?
In the beginning, can you explain why it's a positive IR and not negative if it's going against it?
Here?
Yes.
All right, so this goes back to the previous lecture on currents and resistance, but basically, remember, the whole reason current is flowing is that there's an electric field within these wires. And the electric field goes in the same direction as your conventional current. So if we're going from A to B across the internal resistance, we're going with the E field, basically. And when you go with the E field, there's a negative potential difference.
Oh, that's right.
And then in order to go this way and across the load resistance, we're going against the E field, and that's a positive potential difference. So basically, you can just remember this rule that if you're going across a resistor, there's a voltage drop going with the current, and then a voltage increase going against the current, okay? But that's the reason why, okay? Anything else? Okay, so let's keep it moving. So here's one for you guys to work out. And you can use the equations we've been working with for terminal voltage. That should be enough to do this whole problem actually. But here's the situation. We have a battery connected to a load with a resistance of 465 ohms. When that's our load, the current flowing through the battery is 3 amps. But now, let's take that same exact battery and connect it to a different load with a resistance of 559 ohms. In that case, we'll see that the current flowing through the battery is 2.5 amps. So, of course, we connect it to a larger resistance, we get less current. But the question for you guys to work out is, what is the EMF of this battery and what is the internal resistance of this battery? Okay? So basically, write down one equation which involves this load resistance and this current. Write down another that involves this load resistance and this current, and you should be able to work out the EMF and the internal resistance of the battery, right? So just kind of an algebra problem. See if you can get it, then we'll go through it together. So let me help you get started with just the equations, okay? So remember, we're dealing with a battery which actually has some internal resistance connected to a load. And as we saw previously, the voltage across the whole battery basically just equals the voltage across the load, which gives us epsilon minus I little r equals I times big R, okay? So your first piece of information is when the load resistance big R is 465 ohms, what's the current equal to in that first case?
3.
That's when we have 3 amps of current. So that gives us, I'll call it equation 1, which is this. Epsilon, we don't know that, minus I, which is 3 amps, I'm going to leave the units off, times little r, we don't know that, equals the same I, 3 amps times big R, which is 465 ohms. So that's our first equation, right? Our second equation comes from when big R, the load resistance, equals 559 ohms. What's the current in that case? Yeah, so let's say that gives us equation number 2, which is epsilon minus 2.5 times little r equals 2.5 times big R, which in this case is 559. Okay, so just you have two equations, two unknowns. That's the algebra you have to do. All right? All right, so I'm seeing some people are now getting this, which is great. You should be seeing that the internal resistance little r is 5 ohms, and the EMF is 1410 volts. All right, so just real quick, how can we work this out in the most efficient way? Let's just do equation 1 minus equation 2. The reason I want to do that is because I can get rid of the epsilon factor, okay? Because I'll have epsilon minus epsilon equaling 0. And then I'll have minus 3 minus negative 2.5, so that's plus 2.5, times internal resistance little r. And that should equal 3 times 465 minus 2.5 times 559. Just leaving off the units for convenience here. All right, so what is in my first set of brackets right here? That's minus 0.5 times little r, and then crunch these numbers. What's in my other set of brackets? So if you crunch these numbers, you should find it comes out to minus 2.5. So little r is just minus 2.5 divided by minus 0.5, which is 5 ohms, okay? And once we know that, we can basically, use either equation. Let's say we're going to use equation 1 to get the EMF. So according to equation 1, the EMF is given by, I'll have 3 times 465, and then I'm going to add this term over here, so I'm just solving for epsilon. So I'll add 3 times 5, because that's our internal resistance little r. Okay? So this, if you work it out, is 1410 volts. So there's our internal resistance, there's our EMF. By the way, this kind of thing is going to be pretty commonplace in this chapter. I would say that the equations are usually pretty straightforward to set up. There are a few simple rules that we have to know about how to analyze a circuit. But then the algebra over here wasn't so bad. Other times it can get a little bit messy, okay? But we'll be dealing generally with systems of a couple equations in solving circuits like this, okay? So any questions on what we've done so far? All right then, let's move on to the next topic. Resistors in series and parallel and equivalent resistance. So this should all look very familiar because we've done all of these things when it comes to capacitors. We've seen how to combine multiple capacitors depending on whether they're connected in series or in parallel, and how to come up with some equivalent capacitance for an entire network of capacitors. So it's the same exact game we're going to play, but for resistors. I do want to warn you though, the rules don't come out exactly the same. It turns out for equivalent resistance, the rules are exactly flipped compared to that of equivalent capacitance, as we'll see. So just keep that in mind. All right, so here is the situation we're thinking of. We have some very complex, or maybe a very simple network of resistors connected to a battery, which has terminal voltage V. And this entire network of resistors, whatever they may be doing, is drawing some kind of current from our battery. In other words, there's a current flowing through our battery and then going to that network of resistors. And we're going to call that I. Okay, so V is our battery voltage, and I is the total current being drawn from the battery. But as we know, there may be different currents if we look at each little branch of the circuit. Okay, so I is just the total current coming from the battery. But like before, what we did with capacitors is we can imagine simplifying this network and combining all of these different resistors into a single equivalent resistance. In other words, this is a resistor that if we connected it to the same battery, it would draw the same current as this giant network of resistors. Okay? So this is our simplified circuit. And as you'll see, a lot of problems involve taking the complex circuit and then sort of breaking it down into this simplified circuit. And the equivalent resistance can be related to V and I just by Ohm's law. Remember, this voltage is equal to I times R, and in the case of just a single equivalent resistor, that says V equals I times R EQ. So what I'm going to do next is show you some of the rules that we can employ to go from this picture to this more simplified picture. Okay? So we good on what's going on here? Let's start with resistors in series, and then we'll go to resistors in parallel. So remember, what does it mean to be connected in series in the first place? To be connected in series means all the different resistors are connected along a single conducting path. So you just are connecting with a wire, one resistor to the next, along a single path. If current's flowing, it has to flow through all of them. Okay, it doesn't have separate paths to go down for the different resistors. So the first point I want to make about this situation is that when you have resistors connected in series, they all have the same current. That should be pretty clear just by looking at the picture, but let's try to actually see why that is. All right, so I'm just going to imagine, for the sake of argument, that the resistors did not all have the same current flowing through them. Let's say that resistor number 1 has 2 amps of current flowing through it, and then resistor number 2 has just 1 amp of current flowing through it. What would happen then? Well, let's imagine this point right here connecting the two resistors. Sorry. If they did not have the same exact amount of current flowing through them, then essentially what would be happening is we'd be building up charge at that point. If this was 2 amps and this was 1 amp, we would be building up charge at a rate of 1 coulomb per second right here. But that's not the case. There's no reason charge would accumulate at any of these points connecting the resistors. For that reason, we're going to have the same exact amount of current through all of them. And that's just a feature of different objects connected in series in general. Okay? So what we say is I, remember, that represents the current drawn from the battery. That equals I1, equals I2, equals I3, all the way up to I sub n. They all have the same current, so these are all the same value. On the other hand, let's think about voltages. So voltages are not the same. Voltages add when we're in series like this. And the way to see this is to look at the circuit that I've shown you here and imagine going from point A to point B along two different paths. This is a trick we've used in the past, but basically the idea is if this is point A, this is point B, we can get from point A to point B along two different paths. One of those ways involves going across this battery. And remember, we're calling the battery voltage just V. So the voltage going from point A to point B is just V. We agree? But the other path we could take involves going across all of these different resistors, right? And in this case, if we're going from A to B, we're going against the current. And remember, there's a positive voltage going across a resistor if you're going against the current. But we have to add up the individual voltages of all the different resistors in order to get from point A to point B. So that means V1 plus V2 plus V3 and so on. Just add up as many voltages as you need to all the way out to Vn. Okay? That's why I say the voltages add when you're in series. Okay? The last point to make is about equivalent resistance. And here is where it gets a little different from the rules for capacitors. Remember, capacitors in series, you added the reciprocals of C. In this case, if we have resistors in series, the equivalent resistance is just R1 plus R2 plus R3, and so on all the way out to Rn. So we just straight add the resistances when we're in series. So let me show you why that's the case. So hopefully I've explained this point and you're convinced. Let's actually derive this last equation. All right? Okay. So, what I've shown you is that for series resistors, the voltages add. And that means our battery voltage V equals voltage across the first resistor plus the second plus and so on, all the way out to Vn, okay? So I'm just gonna make some substitutions here using Ohm's law, okay? Remember, by definition, the battery voltage is equal to I, that's the current drawn from the battery, times Req, because this is what we would have if we just had a single equivalent resistor, Req, okay? But for V1, I have the same current. Remember, the currents are all the same, so I don't need to label them differently. I times R1. And for the second one, I have I times R2, and so on. And for the last one, I have I times Rn. And again, the reason I can write it this way is all the currents are the same, and I don't need to label them separately. But clearly, each term in this expression has an I in front of it, so that can just be dropped, which gives us Req equals R1 plus, R2 plus, and so on all the way out to Rn. Okay, so the point is, if your resistors are in series, the equivalent resistance is just the sum of all those individual R values. Okay, that's the rule for combining in series. All right, any questions on that? So I just wanted to show you where that came from. And now that we know where that came from, again, let's summarize. Okay, resistors in series. Currents are all the same. Voltages add. And for the equivalent resistance, we just add the individual R values. Okay, those are the rules. You good? Now let's try to make some sense out of that. I want to show you why it makes sense that if we have resistors in series, that we add the resistances together, and what we get is a larger resistance than any of the individual R values. In other words, we're increasing the resistance by adding more and more resistors in series, right? So if you recall from the last chapter, the resistance of an object is given by this formula. R is equal to rho. That's called the resistivity of the material, times L, that's the length, divided by A, that's the cross-sectional area that the current has to flow through. Okay? Now, by combining resistors in series, which looks like this, effectively what we're doing is increasing the length of that resistive material that the current has to flow through, right? So let's just imagine something simple like two identical resistors, right? They have the same length and they have the same cross-sectional area. So I'm not changing the cross-sectional area that the current has to flow through, because it's the same here as here, but I'm effectively doubling the length. So I should be doubling the resistance, right? Okay, so that's why the equivalent resistance is greater than the individual values, because you have more resistive material, a longer length of resistive material that your charge has to flow through, okay? Any questions on that? All right, let's do, yeah, go ahead.
What the equivalent, when you mentioned the, well, the first one where like the current is the same through all the resistors, I was thinking to the lab that we had where we had the light bulb, like the resistor with the light bulb.
Yeah.
Wouldn't like some, in the case, let's say you had a string of light bulbs like Christmas light, wouldn't some of the current end up getting, I guess, like siphoned away in each resistor due to like the thermal, like you become thermal and light energy, or is that?
Okay, because energy, yeah, certainly resistors consume energy, but they do not consume charge.
Oh, okay.
That's the thing here. Current is just a measure of how quickly charge is flowing through them. So that's not something that's going to be like eaten up in any sense by any of the resistors.
Okay.
Charge is conserved within your circuit. Okay. Good question though. Now let's do parallel. Okay, we've got two types of connections. We have series and parallel. And if we know how to deal with each one, we can simplify many circuits that we'll encounter. So let's do parallel. Now remember, what it means to be connected in parallel is each individual resistor has its own separate conducting path that connects it to the circuit. So now we're thinking of something like what's shown here, where resistor number 1, resistor 2, 3, and so on all have their own separate path for current to flow through. Now, we have a rule for voltage, we have a rule for current, and then we have an equivalent resistance. Let's start with voltages. When you're connected in parallel, voltages are the same. So we can see this by referring to our diagram, where we have, again, a battery, and then connected to that, n resistors in parallel. And we have points A and point B here. Now let's take several different paths in this circuit that go from point A to point B. We'll start with just going across the battery like before. So if we start at point A, end up at point B, the voltage is just V, whatever our battery voltage is. Makes sense, right? Okay, but another path I could take is just to go directly across resistor number 1. You see that? I'm starting at point A, ending up at point B by going across resistor number 1. I'm going against the current, so I have a positive voltage. Let's just call that V1 for now, okay? But if we wanted to, we can call that I1 times R1, just by Ohm's law. All right, another path we could take is going across resistor number 2. That's V2. And you can take the path across any of these resistors, doesn't really matter which one, which is why these voltages are equivalent to each other. So when you have circuit elements, they don't have to be resistors, in parallel, voltages are equal, okay? Any questions on that? Okay, now let's think about currents. Currents are going to add, and the reason for that is pretty straightforward. It's just because charge is conserved within your circuit. So remember, that represents the total current coming off the battery. That's the total current drawn from your battery. Where is that current going? Well, it's basically splitting into all of these separate branches. See, some of this current goes to resistor 1, but some of it goes through resistor 2, some of it goes through resistor 3. There's all these different places for it to go, which is to say that total current I equals I1 plus I2 plus I3 all the way out to IN. Because the current splits from this total amount of current coming off the battery, and it goes all of these different places. That's why, in order to conserve charge, the currents have to add. Does that make sense? Now the last point is this, the equivalent resistance. For resistors in parallel, we're going to add the inverse of the R values. So it's going to be 1 over REQ equals 1 over R plus 1 over R2 plus 1 over R3 and so on. Okay? So remember, this is what I said earlier, the rules for resistors and capacitors are kind of flipped because this is the rule for series capacitors to add the inverses. Okay? So just keep that in mind. Now, I'm going to show you where that comes from. So let's prove that last point. All right. So I've shown you that the voltages are the same for parallel resistors. And I've shown you that the currents add. So let's start with that. Let's start with the fact that the currents add together. This is I equals I1 plus I2 plus I3 and all the way out to I sub n, right? Okay. So I'm going to take this general version of Ohm's law, V equals IR, and solve for I. I equals V over R. And we can essentially apply that for each one of these current terms. But let's explain what that means each time we do it. So on the left side of the equation, I represents the total amount of current flowing off your battery. So that should be your battery voltage, V, divided by REQ, the equivalent resistance of the entire network. For I1, that should be V1 divided by R1. For I2, that should be V2 divided by R2, and that pattern just continues until we hit the last one. But here's the thing, voltages are equal. So this voltage across the battery is the same as the voltage across resistor 1, is the same as across resistor 2, and so on. So that means we can just cancel out these voltages. They're all the same value, right? Which gives us 1 over REQ equals 1 over R1 plus 1 over R2 plus ... 1 over Rn. So that's where this idea that it's the reciprocals of R values that add together. Okay? So that's where that comes from. So to summarize, just to go back to the slide, resistors in parallel, voltages are equal, currents add, and equivalent resistance is given by this formula that we just derived. Okay? Any questions? All right, we'll keep it moving then. So again, I want to give you some intuition for that result that we just derived. Why is it that when we combine resistors in parallel, we're effectively getting a smaller resistance than any of the individual R values, okay? And the reason for that is, go back to this formula. Resistance is resistivity rho times L divided by A. Now, just to make this a simple case, let's imagine, just like before, we have two identical resistors with the same exact material, same exact cross-sectional area, same exact L. Remember, A is the cross-sectional area, whatever this area is here, L is the length here. Now, what we're imagining is current is going to come in, it's going to split, some of the current's going to go this way, some of the current's going to go this way through the bottom and top resistors. That's what it means to have this sort of parallel connection. So effectively, by connecting the two resistors in this way, we're increasing the total cross-sectional area A that this total current is flowing through, right? In this case, we've doubled the cross-sectional area that this current flows through, right? And since A is in the denominator here, we increase it, then we're decreasing the resistance. So combining things in parallel like this effectively decreases the resistance. Make sense? Okay. So here's one for you to work out. Try this. Find the equivalent resistance of this network of resistors. So all of these are given by R. So your final answer should just be some numerical factor times R, right? your answer could be like 5R or 3 halves R or something like that, okay? Basically what I want you to do is try to combine things wherever you see series connections, and then if you see parallel connections, combine those. And at every step, redraw the circuit until you're left at a point where you just have one equivalent resistor, okay? So here, let's go over this together, kind of come up with the game plan, and then I'll let you guys do it, right? What should I combine first? All right, start here. Combine these 3 resistors on the right side in series, okay? Then what do you do next after that? Then this equivalent resistance of these 3 is in parallel with this guy. Then you combine those. And then you'll have 3 series resistors again, and then you'll combine in parallel again. So do those steps, and remember, redraw the circuit at each step just so you can see what's going on. And we'll go through it together in about 5 minutes. Yeah, so for this one, there's going to be a lot of fractions floating around. I think so. Yeah, you got it. That's right. I'm seeing some answers out there. Anyone think they have it? Want to throw their answer out? Some fraction times r is the equivalent of this entire network. What is that fraction?
I got 1/2R, but I'm not entirely confident of that.
That's not quite it. It's close to that.
The 3/5?
Okay, it's actually 11/15. Okay, so let's go through this one, okay? I'm sure you see the steps here. It's just like, you know, we're dealing with a lot of fractions and it's easy to make a simple math error somewhere along the way. So remember, the first thing we're going to do is combine the 3 rightmost resistors in series, because after all, these are all connected along a single conducting path. And that means the equivalent resistance of that set is just the sum R plus R plus R, or 3 times R, okay? So what we'll do next is redraw the entire circuit. So this might take a minute, but just bear with me. All right, so there we go. On the right branch, now we just have a single equivalent resistor, 3R, and the rest are just like before. Okay? So now at this point, it should be clear upon redrawing the circuit that the next step is to combine the 2 rightmost resistors, in this case in parallel. All right, so there's a different rule. We have 1/Req equals 1/R plus 1/3R. Okay? So 1/R can be thought of as 3/3R, right? So if I add that to 1/3R, that's 4/3R. And that means our equivalent resistance is, just flip that fraction to say 3R/4. Okay? Okay, so now we've combined these two, so we'll redraw the circuit again. And now it looks like this. We have R, 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 but this one on the very far right is 3/4 R. Make sense? All right, so now here's what we do. We combine the 3 rightmost resistors. In this case, what kind of combination do we have?
Series.
Series. So that means Req is the straight sum of these 3. R plus 3/4 R plus R again. Okay, so here, let's think about this. R, just think about as 4R/4, right? So we have 4 plus 4 plus 3, 11 R/4. Make sense? So we have 11 R/4. That's the equivalent of these 3. So lastly, redraw the circuit one more time, where we have the 1 leftover resistor R that we haven't dealt with yet, and then 11 R/4. Okay, so the equivalent resistance, when we combine the last two, what kind of combination is this, by the way? Combine the last two in parallel. So now we're going to be using 1/Req equals 1/R plus, okay, just the inverse of this is 4/11R, right? Okay, so 11 is our denominator here. We can think of 1/R as 11/11R. So 11 plus 4 is 15. That's 15/11R. So we flip that fraction to get the final Req. which is where 11/15 came from, okay? So it's a little messy to deal with all these fractions, admittedly, but all of those resistors are equivalent to a single resistor of 11/15 R in resistance, okay? Any questions on that one? So this is a useful strategy is every time you make a combination, redraw the circuit. It helps you keep track of what's going on at each step, okay? All right, so moving on. Here's another one for you. I'm showing you two different circuits where we have a battery connected to two light bulbs. Let's assume that the batteries in each case are exactly the same in their terminal voltage. And let's also assume that the resistances of each light bulb are all equivalent, okay? So in the first circuit, basically what we have is this battery connected to two series light bulbs. And in the second circuit, we have the same battery connected to two parallel light bulbs. My question for you is, which one has a greater total power output? In other words, take the total power output of the two light bulbs in each case, which one is bigger? Okay? We get more total power output when we wire them in series like this or in parallel like this. And this literally translates to brightness, right? So which one is going to be brighter? So try to work this out. Start by combining things according to the rules we just learned about, and then applying the definition of power for a resistor, I squared times R, okay? So take a few minutes and then we'll go through it. How did you figure that? So there's a big resistance, but does not necessarily mean a bigger power. The currents won't be the same, right? That's right. You know the reason why? Can you sort of work out why that is? Just curious how you figured that out.
Is it because it has to go through two resistors and then the other one, it doesn't?
Yeah, but maybe try this. Try to, if you think one's bigger than the other, try to figure out how much bigger. Like twice as big, 4 times as big. That'll force you to just kind of work it out too. So. All right, what do we think on this, everyone? Let's put it to a vote. Okay, who's saying that in the first circuit we have more total power for the series connection like this? Okay, I'm seeing a couple of votes for that. Who's saying it's the parallel connection? And who's saying that they're equivalent? Same power output either way. All right, so we seem to be split on this one, but it is this case that circuit number 2 has a greater total power output. So I'm going to go through this just using equations that we already know, and by considering an equivalent circuit, okay? Because we just have two resistors, they can easily be combined such that our equivalent circuit looks like this. We have our battery and then some equivalent resistance REQ. So if I find the total power output for this equivalent circuit, that will be the same as, analyzing them as two separate objects, okay? So here's what's going on in this equivalent circuit. We just have some current coming off the battery I, And by the way, what is that current? We can solve for it just by using Ohm's law. V is that current I times Req, which means I equals V divided by Req, correct? Then for the power consumed by, both light bulbs, that's going to be I squared times Req. Okay? But in this case, I is given by V over Req, and we're squaring that and multiplying by Req. So what do we have in total? We have the power output of both bulbs is equal to V squared. That's our battery voltage squared, divided by Req. So it's basically going to depend on the inverse of Req. Whichever one has a smaller equivalent resistance is going to give us more power. That's what this is telling us, okay? And actually, right away, we should know the answer. We know it's the parallel connection that gives us a smaller equivalent resistance. We already saw that, but let's just go through the math of it. In the series case, Req is R plus R. We just add them together to get 2R, which means our power is V squared divided by 2R, correct? In parallel, 1 over Req equals 1 over R plus 1 over R. That's how we add these in parallel. So we can say that's 2 over R, right? So that when we flip the fraction, Req is 1/2 of R. So we double the resistance in series, we cut the resistance in half in parallel. That's the idea. So our power is V squared divided by 1/2 of R, which is the same as 2V squared divided by R. So this one is 4 times as large. 4 times as much power in parallel. Okay? Make sense? All right, any questions? All right, cool. So the next thing we're going to do is an example where we put all of these different ideas together. We're going to look at a circuit which consists of a battery and a whole lot of resistors, and they're connected in a complex way. And we're going to solve for the individual currents flowing through each one of those resistors. This is a common type of problem. This is exactly the kind of problem you might see on the quiz, although the quiz is going to be a little bit more simple because time constraints, okay? But it's this type of thing where you have a network of resistors, and what you're trying to solve for is the individual currents flowing through each one. So let's take a look at the problem. All right, so here's what we have. Consider the circuit shown above. The battery provides a voltage of 70 volts. Let's just assume that's constant. Let's not worry about any internal resistance, okay? All the resistors that you see here have the same exact R value, which is 50 ohms, okay? So R1, R2, R3, R4, and R5, all 50 ohms. So here's what we're going to do first. Find the equivalent resistance of all 5. Then find the total current coming from the battery. That's what we call I. And then find the current through each individual resistor. That's I1, I2, I3, I4, and I5. Okay? So the way we're going to go about doing this is start by combining things, and then continue combining things until we just have a single equivalent resistor. That's going to give us Req as well as I. And then we can work our way backwards to find the individual currents, given that we set this up, okay? So let's go through it. Start by labeling the currents, okay? You have your circuit. We're going to label each individual current. And you might look at this and say, well, I already know some of these are the same, but I'm just going to, label things as much as possible so it's absolutely clear. I1, that's the current flowing across resistor 1. I2, I3, I4, I5. So I'm just showing you a current along with each one of these resistors, okay? But if we're trying to simplify the circuit, what would the first move be?
Yeah, minus 4 or 5.
4 and 5, and what type of connection? Series. Okay, what does that tell us about the currents? I4 and I5. They must be the same, right? These are series resistors. They have the same current flowing through them. Okay, because 4 and 5 are in series, here's what we know. I4 is equal to I5, and that's equal to what I'm going to call I45. So after I've combined them into a single object, that single object has the same current flowing through it as these individual objects here, okay? Because we're just talking about current flowing along this branch. It's all the same, all right? Also, since we're going to add those two resistors and combine them into a single equivalent object, R45 is going to be R4 plus R5. Make sense? Because that's how we add things in series. So each one is 50 ohms. So we're just doing 50 ohms plus 50 ohms equals 100 ohms. R45 is 100 ohms. So let's now redraw the circuit, and we'll show the equivalent resistance R45 here with current I45 flowing through it. But remember, this current is just the same as these individual currents here, okay? So hopefully you kind of see what the notation is. It's the same notation we used for capacitors, right? All right, so in order to simplify this further, what's the next move we make? Yeah, so we can do this in a big jump. We can do 2, 3, and 4, 5 all in parallel. We can do them all together. Okay? Do you have a question?
Yes. Can we do R1 or R2 in series?
They're not in series. They're not just connected along a single path because there's a junction right here. Right? That's not a single path that connects them. It splits into two. So that cannot be considered series. Okay? But what we can do is say that these are parallel. Okay? So R2, R3, and R45 are in parallel. What do we know about parallel connections? We know voltages are equal. This voltage across R2 is the same as the voltage across R3, is the same as the voltage across the combination R45. Okay? So that says V2 equals V3 equals V45. Voltages are the same. In parallel, currents, they're not the same, they add. Okay? So what does this say? I2, 3, 4, 5. That means after we've combined all of these into a single object, the current flowing through that object, which I'm calling I2, 3, 4, 5, is equal to the sum of I2, I3, and I4, 5. Because the total current flowing into this combination is going here, here, and here. That's why they add together. All right, the equivalent resistance. We're using the inverses here. So we have 1 over R2, 3, 4, 5 equals 1 over R2 plus 1 over R3 plus 1 over R4, 5. Okay? What are the values of R2 and R3 again? 50 ohms. And then R4, 5, 100 ohms. So we can just directly solve for that. Here's how you want to think about this, okay? Remember, you can't invert each term individually. So I can't say R2, 3, 4, 5 equals R2 plus R3 plus R4, 5. What I can say is R2, 3, 4, 5 equals 1 over R2 plus 1 over R3 plus 1 over R4, 5 to the minus 1 power. So I'm adding these fractions and then taking the inverse of that. That's what I have to do. It's not the same, it's just adding them. So that's 1 over 50 plus 1 over 50 plus 1 over 100 when we plug in the relevant resistance values. Okay? And, okay, 1 over 50, that's the same as 2 over 100, right? So I have 2 plus 1 over 100 to the minus 1 power. That's what I'm dealing with here. So on top I have 5, on the bottom I have 100. But I'm taking that to the minus 1 power. So really it's 100 over 5, which is 20 ohms. Okay, so 2, 3, 4, and 5 have an equivalent resistance of 20 ohms when we combine them all together, all right? But we're not done yet, right? We have to keep combining things. We have to include R1 into this picture. So we're going to redraw the circuit once again and see what we have after we do that. So remember, I have R1. I haven't dealt with that yet, so I'm leaving it alone. And then I have R2, 3, 4, 5. I've combined all of these into a single object, which I'm calling R2, 3, 4, 5. I have current I1 flowing through that resistor. I have current I2, 3, 4, 5 flowing through this equivalent object. That's the idea. You have a question?
Professor, how do we find R2, 3, 4, 5?
Here?
Adding 2 plus 2 plus 1.
Oh, right, because it's 1 over 50 plus 1 over 50 plus 1 over 100, right?
Yeah.
So I'm saying that 1 over 50 is the same as 2 over 100. So I have 2 over 100 plus 2 over 100 plus 1 over 100. That's what this is. And then that's 5 over 100, and the rest follows from there, okay? By the way, I chose the numbers in this problem so that they come out nice and clean. You might see a problem where you don't have nice fractions, in which case just punch it into your calculator and use decimal notation. Just here the numbers come out in nice clean fractions. All right, so here's what we have so far. What do I do next? What is my final step?
R1 and R2, 3, 4, 5 series.
These are in series, correct, which means those aren't actually two different currents. Those are the same current. And it's the same as the current coming from the battery, right? All this stuff is just in one big loop. Everything's in series. So there's the same current for all of these different components. So what that tells us is, since R1, R2, 3, 4, 5, and the battery are all connected in series, remember that's the current coming from the battery, equals I1, that's the current flowing through the first resistor. That's the same as the current I2, 3, 4, 5. That's the current flowing through this equivalent resistance right here. So if we finally want to get to REQ, which is what we have when we've combined everything, you could also write that as R1, 2, 3, 4, 5, but that gets to be a lot of subscripts, so let's not do that. That's R1 plus R2, 3, 4, 5. All right, what's R1?
50.
What's R2, 3, 4, 5?
20.
50 plus 20 is?
70.
50 plus 20 ohms equals 70 ohms. So that's our equivalent resistance for the entire circuit. Okay? All right. So let's just redraw it one more time. Now we have just a battery and a single equivalent resistor. If you recall, the battery voltage is 70 volts. Our equivalent resistance is 70 ohms. So what's the current going to be? It's going to be 1, right? Let's just go through that though. To get the current through the battery, we're just going to apply Ohm's law. V equals I times Req. So to find I, we have V divided by Req. And that's going to be, again, 70 volts divided by 70 ohms, which is 1 amp. Okay, now the rest, here's what we're going to do. We know this current. We can use this along with the other equations we've established along the way to find the individual currents through each resistor. Okay? So this is why we do this process. We simplify things. We say how voltages and currents relate to each other. We write down any equation we know along the way. And then once we get to this, we work our way backwards to get the individual I values. Okay, so this is how that will go. Remember, we already stated that the battery, R1 and R2, 3, 4, 5, all have the same current flowing through them, which means I1 is 1 amp. Right? If the battery has 1 amp of current flowing through it, so does R1, because they're just directly connected to each other in series. But I2, 3, 4, 5 has that same 1 amp of current as well. But this is for the combination. So that 1 amp is going to go and get split into the different resistors in that combination. So to see how that's going to work, we'll remember that for those parallel resistors, we have equal voltages. We have V2 equals V3 equals V45. Okay? And from that, here's what we can say. V2, what is that? It's just given by Ohm's law. It's I2 times R2. Talking about the voltage across a resistor, right? For V3, it's I3 R3. For V45, it's I45 R45. Okay, so we're just applying Ohm's law to each one of these. And so, actually, we have a few different relationships here. See, I'm going to start by just looking at these two. Set I2 times R2 equal to I3 times R3, and then solve for I3. How do you do that? You divide out R3. I3 is equal to R2 divided by R3 times I2. Okay? But what is R2? What is R3? Both 50 ohms? Tells us I2 and I3 are the same, right? I3 is just equal to I2. So that simplifies things, right? Now, we can also do this. We can say, I'm basically going to set this equal to this. I'm going to say I2 R2 is equal to I45 R45. And then I'm going to solve for I45. That's going to be R2 divided by R45 times I2. Basically what I'm trying to do here is eliminate variables. I'm going to try to write everything in terms of I2 so that we can just solve for I2 and then backtrack our way to the others. Okay? So remember, R2 is 50 ohms, R45 is 100 ohms. So we have 50 over 100 times I2, which is a half I2. So to summarize, I3 is the same as I2. I45 is a half of I2. Okay? Good on that point? All right. For that same set of parallel resistors that we've been dealing with over here, with the voltages, we know something about the currents as well. We know that the currents add. Remember, the total current flowing into that combination, which is I2, 3, 4, 5, is equal to the sum of the individual currents. It's equal to I2 plus I3 plus I45. But here's what we're going to do. See, I know this current on the left side. What is this one equal to? This is 1 amp. I also know that I3 is equal to I2, and I also know that I45 is a half of I2. So basically I can just write everything in terms of I2 and then I can solve for it. Okay? So let's make those substitutions. We have I2, 3, 4, 5 equals I2 plus I2, subbed in right here, plus half I2. Just subbed in these last two terms. Okay? Pretty simple. How do I combine these into like a single fraction? What do I have?
Maybe 5 halves.
This is 2 halves plus 2 halves plus 1 half, 5 halves I2. It says I2, 3, 4, 5 is 5 halves times I2. We're trying to find I2, so we'll just say I2 is 2/5 of this one, right? I2 is 2/5. I2, 3, 4, 5. Okay. Got that. So we're talking about 2/5 of 1 amp, right? Which is 2/5 of an amp, 0.4 amps, right? All right, great. So we have I2 now. And the rest are just going to fall like dominoes because we just plug that back into the other equations, right? So for example, I45 is half of I2. So what is that going to be? Yeah, it's going to be half of 0.4, so it's going to be 0.2 amps, right? And I3 is the same as I2, so that's going to be 0.4 amps, right? Also, 4 and 5 have this exact current flowing through them. So we've actually already solved the whole system, okay? Let's summarize what we know. Equivalent resistance, 70 ohms. Got that? I, that's the current flowing from the battery, 1 amp. I1, also 1 amp. 2 and 3 are the same, 0.4 amps. 4 and 5 are the same, 0.2 amps. Okay? That's what we found. Now again, this can get a little complicated, the math can get a little messy, but hopefully what we're doing at each step is pretty straightforward, okay? And if the issue is just keeping track of all this stuff, that's why we redraw the circuit at each step. Can't really go wrong if you do that, okay? Any questions? Okay, so let's take this solution and let's kind of check it. Let's check our answers, verify that it makes sense. The way we're going to verify the answer is to do the following. We're going to see that the total power supplied by the battery equals the total power eaten up by all the resistors. I mean, after all, if we think about the flow of energy in this scenario, you have energy coming from the battery, and it's just going to these different resistors, okay? And the resistors are dissipating that energy in the form of heat and light. So what should be true is that the total power supplied by the battery equals the total power consumed by or dissipated by all the resistors. And if our numbers work out that way, it's a good indication that we did this right. So this is just a way of checking your work, all right? So let's start with this. What is the power delivered by the battery? Well, the battery is not a resistor, so we can't use I squared R, but we can use P equals I times V. That's generally true. So power supplied by the battery is I times V. It's the current flowing through the battery times V, the voltage across the battery. What's the current flowing through the battery? 1 amp. What's the voltage across the battery?
70.
Yeah, it's 1 amp times 70 volts, 70 watts. Okay? So the battery is supplying energy at a rate of 70 watts. Okay? Now, for each individual resistor, we can use I squared R, where I is the current flowing through that resistor and R is the resistance of that particular resistor. We're going to do it for each one separately, because we're trying to make sure that our individual currents came out correct, right? So for example, for our first resistor, we'll have I1 squared R1. What was I1 again? 1 amp. What's R1?
50.
Yeah, so we have 1 amp squared times 50 amps. 50 watts, right? So that's actually telling us that resistor 1 is getting the vast majority of the power, right? As we'll see, when we calculate the other powers, they're very small in comparison. Let's do number 2. It's going to be P2 equals I2 squared times R2. What was our current for number 2? And then the resistance is 50 ohms. They're all 50 ohms, right? So this is 0.4 amps squared times 50 ohms. What does that come out to? 8 watts. P3, I3 squared times R3. Same current, same resistance. That's 0.4 amps squared times 50 ohms. So 8 watts again. Okay, resistor number 4. That's going to be P4 equals I4 squared times I4. And what was current for resistor number 4? That one was only 0.2 amps, if you recall. We still have 50 ohms of resistance. So we have 0.2 squared times 50, which is 2 watts. And then for number 5, it's the same deal, same amount of current, same amount of resistance. 0.2 squared times 50, 2. All right, so 2 plus 8, that's 10. Plus another 2 plus 8, that's 20. Plus 50, that's 70. Okay, so it seems to work out, right? If I sum up the power consumed by all the resistors, it's 70 watts. So whatever the battery is supplying should be eaten up by the resistors, because that's all there is in this circuit, is a battery and some resistors. So current's just flowing from one to the other. Or, energy is just flowing from one to the other, I should say. Okay? Any questions on this? All right, so again, that's just a way of checking your work. It works. Let's do an example. If you know how to do an example like this, you should be pretty good for the upcoming quiz, okay? Yes. So consider this circuit. The resistors are R1 equals 400 ohms, R2 is 500 ohms, and R3 is 700 ohms. This battery has a terminal voltage of 12 volts. We're going to do basically the same thing as before, but it's going to be simpler because there's not as much going on in this circuit. Find the equivalent resistance and find the current flowing through each individual resistor, okay? So try to get this, try to work it out, and then we'll go through it together. How about we do this? There's not that much time left, so here's what I'll ask you to try. Get the equivalent resistance, all right? Do that on your own, and then we'll do the rest of the problem together as a class, okay? So take a few minutes to work that out. You got it. So you got that. Try to do it first. That's the right equivalent resistance, so see if you can get the currents. Good. Looks good. All right. It looks like a lot of you already have the correct equivalent resistance. Can someone tell me what it is?
691.66.
Yeah, so 691.7, if we round it off to a decimal place, 691.7 ohms is what you should be finding. We all got that? So here, let's go through it together now to get the individual currents. Let's do that part. So here's the picture of our circuit. We have a battery, and I'm showing the current coming from that battery as I. Then I have resistor R1. I'm showing the current flowing through that as I1. And then we have I2 and I3 flowing through these two resistors respectively. Okay? So, what's the first thing I notice? What do I combine to start off?
Two parallel resistors, R2 and R3.
Yep, so we'll combine 2, 3 in parallel. And let's just write down every single fact we know about parallel resistances. First should be that if I want the equivalent R23, that's going to be 1 over R2 plus 1 over R3 to the minus 1 power. That's how I'm going to think about that, okay? So we'll plug in what we know. 2 was 500 ohms, so I have 1 over 500 plus 1 over 700, that's R3. And then I'll take that to the minus 1 power, and what does that work out to?
291.66.
Yeah, yep, that's right. So that's the equivalent of 2 and 3. Okay, what else do we know? Just while we're here, they have the same voltage, right? the two parallel resistors have the same voltage, which means V2 equals V3, which means I2 R2 equals I3 R3. That's going to be useful down the line, okay? What about the currents?
They add up, correct?
They add. So what that means is the total current going into this combination, I2, 3, is equal to I2 plus I3, right? The total current flowing in splits into these two paths. So we add those two individual currents to get the total. Makes sense, right? All right, so that's pretty much what we know. The next step is to redraw the circuit, and here's what we'll have when we redraw the circuit. Now what we'll have is the battery connected to resistor R1 with current I1 flowing across it, connected now in series to resistor R23 with current I23 flowing across it. Battery voltage is V, current flowing from the battery is I. But here's the thing. All those currents are the same, right? We're kind of excessively labeling things at this point. Because all these things are in series, the current flowing from the battery is equal to the current going through the current going through R1, and that's the same as the current going through R23. Do we agree? Okay, but actually before we do that, let's talk about how we are going to combine 1 and 2, 3 in series. See, our equivalent resistance, which is R1, 2, 3, is the sum of these two because they're in series. It's R1 plus R2, 3. What's R1? 400 ohms. What's R2, 3? It's what we found up here. 291.67 ohms. So that's where 691.67 comes from. We'd actually want to round that to 691.7 ohms. So that's the equivalent resistance. Okay? Now let's just redraw this one more time. Now we just have a single battery connected to a single resistor, which is the simplest circuit in the world, with current I flowing through both of those things. So here, what we can do, actually, sorry, I jumped the gun a little bit. We said the currents were equal, right, over here. So I just want to make sure we have that down. The currents are equal, which means I, current flowing from the battery, equals I1 equals I23. Okay. So that's just a fact about this circuit right here that I wanted to establish. So now we redraw the circuit and we have this. Okay. We good so far? All right. So using the final equivalent circuit, we can find the current flowing from the battery, because after all, V is equal to our current times the equivalent resistance, which means our current flowing from the battery equals V divided by Req. So what was our V? That was 12 volts. And our equivalent resistance, again, was 691.67 ohms. So what does this work out to?
0.0173.
So it's 0.017349 amps. But here, we're going to round that right here to 3 sig figs, so 0.0173 amps is just fine. Okay? Okay, so next, again, let me just write down that this is the current from the battery. So we haven't really answered the question about the currents going through each individual resistor, but it's pretty simple to get there now that we are at this step. Because after all, I1, that's the same as this current. because if this much current is going through the battery, this much current is also going through resistor 1 because they're just directly connected in series. We also know that I23, the total current going through the 2-3 combination, is equal to this, because those are in series. Remember, that's what we established before. Okay? And we also know that I23 is equal to I2 plus I3, right? We also know from before that I2R2 equals I3R3. So just a little bit of algebra to actually find out what I2 and I3 are. So how about we do it this way? Let's say I2 is R3 divided by R2 times I2. And R3 is 700 ohms. And R2 is 500 ohms. In other words, 7 over 5, which is 1.4. In other words, sorry, I miswrote this. I2 is R3 over R2 times I3. That's what I meant to write, which is 700 over 500 times I3, okay, which is 1.4 times I3. That's what I meant to say, okay? And I'm going to plug that into here, okay? So we have I23 equals I2, which is 1.400 I3, that's the substitution, plus I3, so I23 is 2.400 I3. That means I3 is I23 divided by 2.400, or 0. See, we know the value of this, so let's plug it in. 0.017349 amps divided by 2.400. What's that going to be?
0.00723.
Yeah, so if you do this exactly, it's 0.007229, which rounds to 0.00723. So that's the current through resistor number 3. And then that immediately gives us the current through resistor number 2, because remember, that's just this value times 1.400. So 1.400 times 0.007229 gives us, what is that?
0.1012.
0.01.
Zero.
0.012, yeah, sorry. I get confused saying it out loud. This number. This number right here, okay? Right, so we found the current through I1, the current through I3, and the current through I2. So we have the individual currents. We've solved the circuit. That's how this goes, okay? So let's see how we're doing on time. Okay, not too good. I'm going to show you just a preview of what we're going to do next time. Kirchhoff's rules. Has anyone dealt with these before? If you're an electrician or if you've built electrical circuits before, you've probably come across this, okay? So here's the idea behind Kirchhoff's rules before we wrap up for today. We've already developed a whole bunch of techniques to analyze circuits over the last several weeks. Let me just remind you about what some of those things are. If we have capacitors, we know how to combine multiple capacitors together in series or in parallel. We know now how to do the same exact thing with resistors, okay? But that can only take you so far. That's kind of a limited approach, and it turns out not every single circuit that you encounter can be analyzed just by combining things in series and parallel. There's more to it in certain cases, okay? Sometimes you're not even able to combine things in series and parallel, which means those rules aren't going to, allow you to solve every single problem. So some DC circuits are a little more complex. We're going to learn about Kirchhoff's rules, which can be used when our older methods fail us, okay? It's a much more general way to analyze a circuit. So these are two very, very simple rules developed by G.R. Kirchhoff, who lived in the mid-1800s. And the two rules are the junction rule and the loop rule. Let's go over those two rules, and then we'll end it here. Starting with the junction rule. The junction rule says that the sum of currents entering a junction must equal the sum of currents exiting a junction. So a junction is just where more than two wires meet together, okay? You have some amount of current flowing into that junction. You must have the same exact amount of current flowing out in order for charge to be conserved. That's really the idea behind the junction rule. So it tells you how to deal with multiple currents meeting at a single point and how they relate to each other. The other rule is called the loop rule. This says that the sum of changes in electrical potential around any closed loop of a circuit must equal 0. So this says, take a look at your circuit, identify some kind of loop in that circuit. It can be any loop at all that you choose. And if you go across each of the circuit elements and you find your delta V, you find your potential difference. You could be going across a battery, you'd be going across a capacitor, going across a resistor, going across various elements. But if you sum up those potential differences in a loop, meaning you end up exactly where you started, that's always going to equal 0. And if you use these two rules together, you can basically tackle any DC circuit, okay? So we'll learn about how to do that in detail next time, right? Next lecture is all about these two rules.